The last part of Chapter 28 deals with two special statistical distributions, the binomial distribution and the Poisson distribution. And the binomial distribution is something we're familiar with already. It involves two outcomes. This is the formula for it. The notation used to denote that it's a binomial distribution, we say that x is distributed as b and then n comma p. N is the number of items, p is the probability of a success. And we can do binomial calculations in our calculator. We do second and then distributions. And in the calculator where that is, it's second, at least on the TIs, and then the variables key right above here, distribution. And here are these normal we can come down here, there are the binomial distributions. And you'll see here there's also Poisson distributions. The PDF, the probability density function, is when we're finding the probability that x is equal to some number. We can use the cumulative distribution function when we're dealing with the random variable being less than or equal to some number. And to be a binomial distribution, they're discrete, they're countable, they have two outcomes, and all the trials are independent. So here we have a binomial problem. 72% are in favor of a change. We sample 5 people, find the probability that at least 3 of the 5 members are in favor. So here x is represented by a binomial distribution where n is 5 and the probability of a success is 72%. And what we're looking for is the probability that x is bigger than or equal to 3. So 3 or 4 or 5. Remember, this is discrete, it's not continuous. So 3, 4, 5. And that's the same as 1 minus the probability that x is less than or equal to 2. And now that we have the probability phrased this way, we can use our calculator and use the cumulative density function. And this is what we'll type in, 5, 0.72, 2, because 2 is the value of r, it's the value that x is less than. And when we do that, we end up getting a probability of 0.862. The parameters we have for a binomial distribution, the mean is equal to n times p. And the standard deviation is the square root of n times p times q. So here's another binomial problem. Find the mean and standard deviation of the number of defects in the sample. So number of defects, that means that this 5% is p. Here, this is a binomial distribution where n is 80 and p is 0.05. So the mean .05 times 80, which is 4. This is also the expected value. Another way to think of this. Standard deviation is the square root of 80 times 0.05 times 0.95, the probability of not getting a defect. And that's approximately 1.95. The Poisson distribution is basically the limit of the binomial distribution. It's what happens over time to this binomial situation. So as n gets really, really big, this is what it becomes. And this does not do a good job for small values of r, for a small number, for a small value of x. Some examples of when this might be used would be the number of phone calls per hour coming into a call center, or the number of fish caught per day in a lake, number of car accident per month on a certain stretch of road. The m here is called the parameter of the distribution, and m in a Poisson distribution ends up being the same as the mean and the variance. They're all equivalent. And the notation that we use, x is distributed as PO parentheses m. This distribution, the only parameter that we need is this m value. So x stands for the number of errors on a page, and 80 pages were sampled. Here, the number of pages with 0 errors were 3, 1 page was 11, 2 pages is 16, 3 pages is 18, 4 pages have 15 errors, or 4 errors show up 15 times, and this continues on. The mean number of errors ended up being 3.2125. It says, using a Poisson distribution, what is the probability generating function? So the probability that x is equal to any particular x value is equal to e to the negative 3.2125 times 3.2125 to the x over x factorial. And now this is saying, does this generator effectively model our data? And we can check that using our calculator. Now what I'm going to do is I'm going to go into my list editor, and into L1 I put these lists, these x values 0 through 4. List 3 is the probability that goes along with each of these. I took 3 divided by 80, 11 divided by 80. So the probability that we get one error experimentally is 0.1375. Now what I'm going to do is I'm going to put in this generator function. E to the negative 3.2125 times 3.2125. Now I'm not going to put x. What I'm going to do is I'm going to put list 1 as my exponent. This is just going to reference whatever's in list 1 that matches up with each element here, divided by list 1 factorial. Push enter, and note the similarity between list 2 and list 3. We're very close. This Poisson distribution does effectively model the data that we've collected, and there is a formal test to decide if a Poisson distribution is appropriate. We're not going to cover it in the core part of IBSL. It is covered in the optional topic, and those of you that have taken AP Stats have probably dealt with this before. But for our intents and purposes, our problems are going to tell us this variable is distributed with a Poisson distribution, and we'll know to reference this formula. So here's the assignment to go along with this.